This video is about using augmented reality to represent the effects from the relativistic Doppler shift at non-relativistic speeds. The relativistic Doppler effect is a set of combined effects together. So first of all, you have the regular Doppler effect. Then you have something that comes from time dilation. And then there's this third component, which comes from length contraction and how that impacts angles. And so that would be known as the relativistic aberration. So this is an angular dependence due to relativity. Oftentimes when using light, rather than saying that the frequency increases or decreases, people say that it has a blue shift or a red shift. So a blue shift would be an increase in frequency or equivalently a decrease in wavelength. And a red shift would be a decrease in frequency or equivalently an increase in wavelength. So I just want to take a moment to talk about color theory. So there's a pretty big distinction between color in physics and color in kind of everyday life. And so in physics, we tend to think in monofrequency terms. So you have a set of frequencies and those are the visible, all on a line. When we talk about light in our everyday lives, is that there are a bunch of colors that are composite colors. So they combine a bunch of these different frequencies together to get you very unique colors. So there's things that in the physics realm of colors don't exist, but exist as everyday colors. So things like pink or some other types of composite colors like brown and stuff, you might not actually find on a rainbow. We have to find a way of connecting the frequency that we're getting from our phone information to be able to do this frequency shift to get some sort of meaningful information. And so there's a few different ways that you can do that. The way that I'm going to do that for simplicity's sake is I'm going to use a color system known as HLS, which is hue, saturation, and lighting. In this particular color space, it's really nice because you can just change the hue of a color, and the hue does roughly represent a rainbow. So there's kind of an almost equivalence between physics rainbow and hue rainbow. And so you'll end up with kind of the right coloration shift. And then the other thing that's a little bit nice about that is that if you did this with just straight RGB, you might end up with some scenes that don't look real anymore. So you might end up with kind of just like a blotch of blue or a blotch of red. But this will make it so that it just appears like you're filtering the image in this color rather than actually just kind of erasing the image and just having blue or red for the blue or red shift. So that's why we're going to be using hue. One of the problems with this is that when you use HLS, you are not changing the brightness or darkness of anything. And in particular, when we start going very, very fast, there would be a darkening of things that are redshifted enough. Once things become redshifted enough, they go out of the visible. And same with if things get blue shifted enough, they leave the visible spectrum. So things that are especially red or especially blue should actually be appearing much darker. That's something that is not physical in our model, but is a real effect that happens. Things get darker as you travel faster in certain areas of the sky, and other areas will get brighter because you are shifting things that were not visible into the visible spectrum. So I was going to do an example outside in Saskatchewan and have all these colors, and then I just realized that Saskatchewan at this time of year has no hue whatsoever outside. The sky is gray, the ground is gray, there's some brown, no hue. So we'll have to leave that for later. So you might notice as we start going a little bit faster, there'll be a circle that starts forming. It might actually be a little bit misleading how we've done some of this. Anything outside of that circle would actually appear much darker. And so that's because we're going so fast that anything that starts reaching us from other directions will be so redshifted, it will be hard to see. So because we are only redshifting hue and we're not redshifting the other values, it doesn't actually darken the color. But in reality, you would end up kind of having this rainbow porthole, and anything outside of the rainbow porthole would be very dark. So you might still get some pieces of light from high energy sources, but anything outside of those high energy sources will be so redshifted that you just won't be able to see them. We're going to start from the camera access project that we did. So to start off with, we're just going to initialize a few values that have to do with limiting the velocity that we have. And yeah, so then what we do is we construct a mesh. So we're basically going to be hovering a mesh in front of the camera. And so to do that, we need to get the values of the mesh and then just position it so that when on each frame, it'll update to be exactly in front of the camera. So that's this camera and distance to camera. And so that makes it so that it'll cover perfectly our visuals. Then what we're going to do is add in the mesh and add some shaders to it. So we need to add all the different values that the shader will hold. So the things that we need to give the shader program is going to be the direction, the velocity, the camera image, the velocity in a vector form, and then some positional informations about how large the canvas is and how large our geometric mesh is. And that'll help us get the right information so that we can do the trigonometry and geometry that we need to get the correct redshift. And then we'll add in our texture shaders. The next thing that we need to do is we need to update these every single frame that happens. So how you do that is you look at each position and then you find the difference between that. So we are finding the numerical velocity by picking two positions and then finding the difference and then dividing that by a time value. And then we're scaling this by a certain amount because we need to be able to get an accurate representation of how fast it's moving. We need to scale it so that it is within the speed of light. So basically what we're calculating here is beta. Because we are not actually going near the speed of light, and because a lot of these equations fall apart past the speed of light, we need to find some sort of way of converting our speed, our kind of movement through space, into a relativistic speed. So something that will be equivalent to these higher speeds. So there's a few ways of doing this. One way you can do is you can make like a clamping function, which just turns all of your speeds into a set number of speeds and do that sort of transformation. Another way is a sigmoid function. So that will make it so that you will asymptotically approach the speed of light, but you won't ever quite get there. And so that's kind of a nice solution because it will show the dynamics as you go fast. So I like the idea of using a sigmoid function, but there's a bunch of other ways you can do this. This is a really artificial part of our construction of this model. So it's not, you can do however you want. And then every frame, there's also a few values that need to get updated. So this is probably the most complicated shader we've looked at yet. So to start off with, we need to initialize all the values that we're giving to it. And then we will initialize a RGB to HLS and an HLS to RGB function. Then we need to get our values for our pixels from our camera. So that is the U sampler is the image, and then that's a coordinate that we're getting to that. And so that'll give us, each shader valuation will give us a color. And then this color, we are changing to HLS. HLS, we are taking out the hue information. Then we are calculating out the local pixel direction. So even though we have a general direction, each pixel will have like an additional vector associated with that, away from the direction is kind of the middle of our screen straight forward. And so we need to do a little bit of a calculation to measure the pixel difference between our direction and that direction. And then that will give us cos theta when we combine it with difference between our velocity and the pixel direction, which will give us the cos theta. And then we can calculate a gamma with our velocities. So the vel in this case you can see as being a beta, because it has been scaled now so that it should be like more like a beta. And then we can just calculate out the Doppler shift. And once we have that value, we can clamp it so that it doesn't, if you notice the hue value, actually the highest frequencies or the highest hues are actually back to red. So we need to kind of cut off that little bit so that the highest frequencies are purple. And this will give us a little bit of a shift if we are not moving. So with special relativity, there is a few other aspects that we could look into in the future. So today we did the Doppler effect with the real world. I also wanted to look into whether we can do length contraction, and I think that's possible, but I think it'll be a little bit messy. I don't think it'll look as nice as I would like. We can also apply these effects in the digital world too. So on a digital scene with 3D objects, like 3D digital objects, time dilation, I don't know how I would approach that. That is like, you can do it in the digital world by like taking a bunch of records and then shifting the, like if you have everything on a different clock, you can kind of get away with doing it in the digital world, but like how would you do that in the real world? Like you'd have to like take videos and do a bunch of video splicing in real time, and but you couldn't do it. You'd have to do it so that your phone was the fastest reference frame. I don't know. I think it's impossible. And then there's also a bunch of other aspects that you can do. So special relativity, even though these are the three things that you oftentimes focus on, you can do acceleration measurements, and then there's also things with rotations, and especially when you start combining Lorentz transforms together, you can get some really interesting things going on. But I think we're just going to leave that for the future because that's a little bit too much to think about right now. Yeah.